There is a place in the universe where a star collapses into an object smaller than a city, yet outweighs the sun. There is a planet where it rains iron, sideways, in the dark. There is a sound echoing through space from an event so ancient that nothing alive today can trace its origin. And there is an object so massive, so completely inexplicable, that the very best models of how the universe works cannot explain why it exists at all. These are not hypotheticals. They are confirmed observations, sitting in scientific literature, made by instruments humans built and pointed at the sky. The universe did not consult our expectations before building itself. This is why the strangest discoveries in space keep arriving not as distant possibilities, but as verified facts, each one quietly dismantling something we thought we understood. Before we begin, be sure to like the video and subscribe for more journeys into the cosmos. Now, take a deep breath and let's begin. The universe is roughly 13.8 billion years old. In that time, it has assembled itself into structures of staggering complexity, galaxies, clusters, filaments of matter stretching across hundreds of millions of light years. And in all that time, across all that space, it has also built some things that don't fit neatly into any category we know how to describe. Some of the strangest confirmed objects and phenomena in space fall so far outside intuition that even physicists with decades of experience reach for words carefully when discussing them. What follows is a journey through those objects. Not the merely exotic pulsars and black holes have become almost familiar at this point. These are the things that made astronomers stop, look at their data again, and quietly wonder if they had misunderstood something fundamental. Start with the simplest category: objects that shouldn't exist at the scale they do. The universe has a speed limit for how quickly information can travel. It also has a rough timeline for how quickly structures can form. In the very early universe, matter was spread nearly uniformly, with only the faintest density variations seeded by quantum fluctuations. Gravity then slowly pulled matter together, condensing it first into stars, then galaxies, then clusters, then the large-scale web of filaments we see today. That process takes time, and the amount of structure that can form is fundamentally limited by how long gravity has had to work, which makes what astronomers found in 2012 genuinely difficult to absorb. The Huge Large Quasar Group, known as the Huge LQG, is a collection of 73 quasars spread across a region of space roughly 4 billion light-years across. It is not a loose association. These quasars are gravitationally connected, forming what astronomers classify as a coherent, large-scale structure. 4 billion light-years. The observable universe is about 93 billion light-years in diameter, which means this single structure spans roughly 4% of everything we can see. That number is a problem. The cosmological principle, one of the foundational assumptions of modern cosmology, states that on sufficiently large scales, the universe should look roughly the same in all directions and from all locations. Structures larger than about 1.2 billion light-years should not exist, because above that scale, the universe becomes statistically smooth. The Huge LQG is more than 3 times that theoretical upper limit. It should not be there. There have been debates among cosmologists about whether it constitutes a true bound structure or a statistical artifact, but the quasars are real, their clustering is real, and the challenge it poses to homogeneity models has not been quietly resolved. It sits in the literature as an open question, a structure that arrived before it was supposed to, at a scale that challenges the framework used to describe everything else. And there is another candidate structure that pushes the problem even further. The Hercules Corona Borealis Great Wall is a proposed superstructure identified through the clustering of gamma-ray bursts at a redshift of around 2. If the clustering is genuine, if these bursts are tracing a coherent large-scale structure rather than a statistical fluctuation, the structure spans approximately 10 billion light-years. That is more than 10% of the entire observable universe. The theoretical maximum for coherent cosmic structures, based on how long gravitational attraction has had to operate since the Big Bang, is roughly 1.2 billion light-years. 10 billion is roughly 8 times that limit. The debate about its reality centers on statistics. Gamma-ray bursts are relatively rare events. The apparent clustering could be a chance fluctuation in where those bursts occurred, combined with selection effects in how they were detected. More data will eventually resolve the question, but the structure has appeared in multiple analyses, survived multiple statistical tests, and has not gone away despite scrutiny. If it is real, it means the universe is structured on scales that existing theory simply cannot produce. The scaffolding underlying our current cosmological framework would need to be re-examined at its foundations. Either way, whether it dissolves under further analysis or persists, the fact that an object of this claimed scale exists in the literature without a clear resolution illustrates how far observational capability has outpaced theoretical expectation. Not all large structures in the universe are filled with matter. Some of the most significant features in the cosmos are defined by what is missing. The Boeda's void, sometimes called the Great Nothing, is a roughly spherical region of space, about 330 million light-years across, located about 700 million light-years from Earth, where you would expect to find thousands of galaxies based on the surrounding average density. The interior of the Boeda's void contains almost nothing. When it was discovered in 1981 by Robert Kirshner and colleagues, the result was so unexpected that Kirshner reportedly remarked it looked like the universe had a hole punched in it. Voids are not unusual. The universe's large-scale structure consists of a cosmic web where galaxies and clusters occupy filaments and sheets surrounding vast, underdense regions. But the Boeda's void is unusually large and unusually empty, even by the standards of cosmic voids. Standard simulations of cosmic structure formation can produce voids of this size, but barely and only under particular assumptions about dark matter and dark energy. More recently, surveys have mapped what appears to be an even larger structure, the cold spot supervoid, a region of lower than average density aligned with an anomalously cold patch in the cosmic microwave background. The cold spot in the CMB is itself one of the most debated anomalies in cosmology, a region roughly 14 degrees across in the southern sky that is colder than the surrounding background by an amount that is statistically unusual. Several explanations have been proposed. One is purely statistical, in a full sky map of CMB fluctuations. Some fluctuations will be unusually large by chance, and the cold spot may simply be one of them. Another is physical. A supervoid in the foreground could create a temperature decrement through the integrated Sachs-Wolf effect, where photons from the early universe lose energy as they climb out of the gravitational potential of the void. Observations have confirmed a supervoid in the direction of the cold spot at a redshift around 0.2, but whether it is deep enough and large enough to explain the full temperature deficit remains disputed. The cold spot is one of several anomalies in the CMB that are difficult to explain within the standard cosmological model. Another is the hemispherical asymmetry, the fact that fluctuations appear slightly stronger on one half of the sky than the other, a feature that shouldn't exist in a statistically uniform universe. Another is the alignment of the lowest order CMB multipoles, the largest scale temperature patterns with each other and with the ecliptic plane of the solar system, which also shouldn't happen by chance if the universe is truly isotropic. These anomalies might be statistical flukes. They might be systematic effects in how the data was processed. Or they might be hints of something real physics, operating on scales large enough to leave an imprint on the earliest light in the universe. The Planck satellite, which produced the most precise CMB maps ever made, confirmed that the anomalies are present in the data even after careful treatment of systematic effects. They remain unexplained. Move a little closer in cosmological terms, and things get stranger in a different direction. Quasars are among the most luminous objects in the universe. They are powered by supermassive black holes actively consuming material, releasing energy in quantities that can outshine entire galaxies. The black holes at their centers are enormous, some exceeding several billion times the mass of the Sun. But the most extreme quasars discovered in the last decade have pushed mass estimates so high that astronomers have needed to revisit fundamental assumptions about how black holes form and grow. In 2019, a quasar designated J03131806 was confirmed at a redshift that places it when the universe was less than 700 million years old, roughly 5% of its current age. At the center of this quasar sits a black hole with a mass of 1.6 billion times that of the Sun. To understand why that number is strange, consider how black holes grow. A black hole accumulates mass by consuming surrounding material. There is a theoretical upper limit to how quickly it can do this. The Eddington limit, based on the balance between gravitational pull inward and radiation pressure pushing outward on infalling material. If a black hole grew as fast as physics allows consuming material constantly, at the Eddington limit, with no interruption starting from the very first stars in the universe, it still could not reach 1.6 billion solar masses in under 700 million years. Not even close. Starting from a stellar mass black hole of around 100 solar masses and accreting at the maximum theoretical rate without pause, you get perhaps a few 100 million solar masses at that age, under the most generous assumptions. 1.6 billion requires either a much larger seed, a much faster growth rate, or both. Neither option has a comfortable explanation. Seed black holes of the mass required are not predicted by standard stellar physics. Sustained super-Eddington accretion for hundreds of millions of years is theoretically possible in some models, but has never been observed and is difficult to sustain. Each new ultramassive quasar discovered at high redshift adds another data point to a problem that doesn't have a clean solution. The universe, apparently, found a way to build something enormous, far faster than the rules we derived from everything else suggest it should have been able to. One proposed resolution involves direct collapse, black holes, objects formed not from the collapse of individual massive stars, but from the direct collapse of massive clouds of primordial gas in the early universe, bypassing stellar evolution entirely. If conditions were right, if the cloud was large enough, if cooling was suppressed to prevent fragmentation into individual stars, the collapse could produce a seed black hole of 10,000 to 100,000 solar masses directly. From such a seed, reaching 1.6 billion solar masses in 700 million years becomes more plausible. But direct collapse black holes have not been confirmed observationally. There are candidate objects in recent James Webb Space Telescope data that some researchers interpret as direct collapse black hole hosts, but the evidence is not yet definitive. The problem of how the universe built its most massive black holes so quickly remains open. When a massive star reaches the end of its life, the sequence of events is well understood. The core collapses. If the mass is right, the outer layers rebound in a supernova explosion. What remains is either a neutron star or a black hole, depending on the initial mass. Below a certain threshold, you get a neutron star. Above roughly 3 solar masses of remnant core, nothing can stop the collapse, and a black hole forms. That boundary has been considered relatively well established for decades. And then came the object GW 190814. In August 2019, the LIGO and Virgo gravitational wave detectors picked up the signal of a merger. One of the objects involved had a mass of approximately 23 solar masses, a black hole, unremarkable in that context. The other had a mass of approximately 2.6 solar masses. That second object fell squarely inside what astronomers call the mass gap, the range between roughly 2.5 and 5 solar masses, where neither neutron stars nor black holes were expected to exist. Neutron stars, at the heavy end, top out around 2 to 2.5 solar masses before their internal pressure can no longer resist gravity. Black holes, at the light end, were not thought to form below about 5 solar masses through normal stellar evolution. 2.6 solar masses sits right in the middle of that gap. The object was either the heaviest neutron star ever detected by a significant margin, or the lightest black hole ever detected by a significant margin. Distinguishing between the two would require knowing whether it had a hard surface, a neutron star property, or an event horizon, which would make it a black hole. The gravitational wave signal alone cannot resolve this. The merger produced no detectable electromagnetic counterpart, so there was no light to study. The identity of the 2.6 solar mass object remains genuinely unknown. What it represents is a confirmed gap in understanding, a region of the mass spectrum that existing stellar physics says should be empty, occupied by something that definitely exists. And GW 190521 pushed in a different direction entirely. Detected in May 2019, this gravitational wave event involved the merger of black holes of approximately 85 and 66 solar masses, producing a remnant of around 142 solar masses. The 85 solar mass black hole was itself a puzzle. In that mass range above about 50 solar masses, a phenomenon called pair instability is expected to prevent massive stars from collapsing directly to black holes. In stars above a certain mass, the core temperatures become high enough that gamma rays spontaneously create electron-positron pairs. This drains energy from the radiation pressure supporting the star, causing partial collapse and explosive episodes that expel large amounts of mass before a final collapse. The result is that stars in this mass range are expected to shed enough mass before the end of their lives that their remnant cores fall below the threshold for forming black holes above about 50 solar masses. An 85 solar mass black hole should not easily exist as a first-generation product of stellar evolution. One interpretation is that it was itself the product of a previous merger, a second-generation black hole, formed when 2 smaller ones collided in a dense stellar environment, like a globular cluster or the dense core of a young massive star cluster. Such hierarchical mergers, black holes merging to form larger ones, which then merge again, were predicted theoretically, but had never been directly evidenced before gravitational wave detectors went online. GW 190521 is tentative observational evidence that this process is real and occurring. The universe contains objects that spin. Stars spin. Black holes spin. Neutron stars spin. But the rate at which some of these objects rotate pushes so far past intuition that the numbers require a moment to sit with. PSRJ 17482 446 AD is the fastest spinning pulsar currently confirmed. It completes 716 full rotations every second. 716. The equator of this object, a sphere roughly 20 kilometers across, containing more mass than the Sun, moves at approximately 74,000 kilometers per second. That is roughly 24% of the speed of light. And it does this continuously, with a precision that rivals the best atomic clocks humans have ever constructed. Pulsars like this are called millisecond pulsars, recycled neutron stars that were spun up over millions of years by material flowing in from a companion star. That infalling material transferred angular momentum to the neutron star, gradually accelerating it the way pushing on a spinning top speeds it up. The result is an object so stable in its rotation that astronomers use them as precision instruments, natural clocks distributed across the galaxy to detect things that otherwise leave no observable trace. When a gravitational wave passes through space, it stretches and compresses distances. If a pulsar is at a known distance with a precisely known rotation rate, a tiny, regular shift in the timing of its pulses reveals the passage of a gravitational wave with wavelengths spanning light years. This technique, called pulsar timing arrays, recently produced the first strong evidence for a gravitational wave background, a low-frequency hum permeating the cosmos, generated by pairs of supermassive black holes slowly spiraling together in the cores of distant galaxies. The fastest spinning object in the universe is also one of the most sensitive instruments ever used. But speed is not the only extreme property of rotating compact objects. Black holes carry angular momentum in a way that has observable physical consequences. A rotating black hole is described by the Kerr metric in general relativity, a solution to Einstein's field equations that differs significantly from the non-rotating Schwarzschild solution. A rotating black hole drags space-time around with it, an effect called frame dragging. Material orbiting close to a rotating black hole doesn't just orbit, it is swept around by the rotation of space-time itself. The innermost stable circular orbit, the closest point at which matter can orbit without spiraling in, is smaller for a rotating black hole than for a non-rotating one, and its location and properties are sensitive to the spin rate. Measurements of the iron emission lines in the X-ray spectra of material orbiting close to black holes in X-ray binary systems have been used to infer black hole spin rates. Some black holes appear to be spinning at very close to the maximum physically allowed value, near a maximally spinning black hole. The effects of frame dragging are so extreme that even photons traveling in the retrograde direction against the spin are dragged forward. The ergosphere, the region just outside the event horizon where this dragging is unavoidable, allows in principle for energy to be extracted from a spinning black hole's rotation through a mechanism called the Penrose process. Black holes, by the most fundamental interpretation of general relativity, are not static objects. They have spin, and that spin influences everything around them. In 2019, the Event Horizon Telescope published the first direct image of a black hole's shadow, the supermassive black hole at the center of Messier 87. 6.5 billion solar masses, surrounded by a bright ring of glowing gas. 2 years later came the image of Sagittarius A, the 4 million solar mass black hole at the center of our own galaxy, 27,000 light-years away. What made these observations so significant was not simply that they confirmed the existence of something previously inferred. It was the precision with which the images matched the predictions of general relativity. The asymmetry and the brightness of the ring around the black hole in Messier 87 brighter on one side is caused by relativistic beaming. The part of the disk moving toward us appears brighter due to the Doppler effect. The shadow size, the ring thickness, the brightness distribution, all matched within the margins of measurement and uncertainty. To resolve the detail needed for those images, the Event Horizon Telescope used a network of radio telescopes spread across multiple continents, effectively creating an Earth-sized telescope dish. The resolution achieved was comparable to resolving detail the size of a grain of rice placed on the surface of the Moon, observed from Earth. But there is something worth sitting with about what those images actually show. The event horizon is not a surface in the usual sense. It is a mathematical boundary, the point from which no information can escape. Cross it, and you have left the observable universe behind, not in the sense of traveling away from it, but in the sense that no signal you send can ever reach anyone outside again. What happens inside the event horizon is beyond the reach of observation by definition. General relativity predicts a singularity, a point where density becomes infinite and the equations of physics break down. But physicists widely believe that the singularity is not real. It is a signal that general relativity has been pushed beyond its domain of validity. At the densities and curvatures inside a black hole, quantum effects must become important. And a consistent theory of quantum gravity, one that seamlessly combines general relativity and quantum mechanics, does not yet exist. The images from the Event Horizon Telescope confirmed the geometry of the event horizon with extraordinary precision. But the deepest questions about black holes remain unanswered. One of the most debated is the black hole information paradox. Quantum mechanics requires that information is never truly destroyed. Processes at the quantum level are reversible in principle, and the information about how a system was arranged is always preserved somewhere. But when matter falls into a black hole, its information appears to be lost. And when the black hole eventually evaporates through Hawking radiation, the slow emission of thermal radiation, predicted by Stephen Hawking in 1974, the radiation carries no information about what fell in. The information appears to have vanished. That violates a fundamental principle of quantum mechanics. This is the information paradox, and it has occupied some of the most capable theoretical physicists for decades without resolution. Some proposals suggest the information leaks out slowly through subtle correlations in the Hawking radiation. Others suggest it is encoded on the event horizon in some form and released at the end of the black hole's life. Others suggest the paradox is resolved by modifications to general relativity near the singularity that we don't yet understand. None has achieved consensus. The information paradox is a signal that two of our most successful physical theories, general relativity and quantum mechanics, are fundamentally incompatible at the extremes of black hole physics. Whatever resolves, it will require a new framework. On a different scale entirely, the variety of exoplanets discovered since the 1990s has systematically dismantled the template built from our own solar system. Our solar system has small, rocky planets close in, gas giants further out, and relatively circular, well-separated orbits. That pattern, it turns out, is not the universal default. The first confirmed exoplanets around a sun-like star were hot Jupiters, gas giants, orbiting so close to their stars that they complete a full orbit in days. Their existence was immediately puzzling because the standard model of planetary formation predicts that gas giants can only form in the outer regions of a solar system, far from the star where volatile ices can exist in solid form and accumulate into planetary cores. A gas giant shouldn't be able to form where hot Jupiters are found. The resolution is migration. Gas giants can form at large orbital distances and then lose energy through interactions with the disk of gas and dust surrounding a young star. spiraling inward over millions of years until they reach their final close-in orbits. But the implications of that migration for the rest of the planetary system are severe. A gas giant, migrating through the inner solar system, sweeps up and ejects smaller planets in its path. Systems that host hot Jupiters tend not to host Earth-like planets in inner orbits. The diversity of orbital configurations observed in exoplanet surveys is remarkable. Multi-planet systems, with all planets packed into orbits smaller than Mercury's orbit around the Sun. Systems with massive planets on highly eccentric elliptical paths. Systems with planets orbiting in the reverse direction from their star's rotation. Each configuration represents a history of formation and dynamical evolution. And the sheer variety suggests that the ordered, well-spaced arrangement of our own solar system may be somewhat atypical. Consider WASP 76b. This hot Jupiter orbits extraordinarily close to its host star, completing a full orbit in less than 2 Earth days. WASP 76b is tidally locked, meaning one side permanently faces the star and one side permanently faces away. The dayside temperature reaches approximately 2,400 degrees Celsius. That is hot enough to vaporize iron. Iron vapor, carried by the extreme atmospheric circulation from the day side to the night side, eventually reaches the cooler terminator, the boundary between the permanent day and permanent night hemispheres. On the night side, it condenses and falls as rain, iron rain. The Very Large Telescope's espresso spectrograph detected the spectroscopic signature of iron vapor on the day side and its absence on the night side, consistent with a scenario where iron condenses and precipitates out of the atmosphere before reaching the morning terminator. Iron falling from the sky, driven by the geometry of a world too close to its star to ever see a dawn. Then there is HD 189733b, another hot Jupiter, one of the most studied exoplanets in history. Its blue color, detected through transit observations, is not caused by liquid oceans or scattered sunlight. It comes from silicate particles in the atmosphere, condensed glass droplets suspended in clouds at temperatures around 900 to 1,000 degrees Celsius. Those glass clouds are blown by winds measured at speeds exceeding 8,000 kilometers per hour, and they create a horizontal rain of glass and silicate particles that shoots across the atmosphere at those speeds. Glass, in the wind, at thousands of degrees, moving fast enough to cross a continent in minutes. Both of these planets have been studied by multiple instruments, multiple research groups, across multiple observation campaigns. The rain of iron and glass on distant worlds is as confirmed as the existence of the worlds themselves. Then there is the quieter strangeness of the super-Earth's planets, with masses between 1 and 10 times Earth's mass, a category that simply does not exist in our solar system. The gap between Earth, at 1 Earth mass, and Neptune, at 17 Earth masses, is empty here. But in the rest of the galaxy, super-Earths are one of the most common planet types found around Sun-like stars. Their nature is ambiguous. Planets in this mass range could be large, rocky worlds with thick atmospheres, scaled-up versions of Earth. They could be small water worlds, their bulk composed largely of ice and liquid at high pressure. They could be mini Neptunes with substantial hydrogen-helium envelopes. Some have densities suggesting large water fractions, but at the temperatures they orbit their stars, water cannot exist as a surface liquid. It would form a supercritical fluid, a state with properties of both liquid and gas simultaneously, under immense pressure. Planets with surfaces, if they can be called that, made of supercritical water at thousands of degrees and enormous pressures, a world where the ocean and atmosphere are indistinguishable, where no solid ground exists, where the phases of matter merge into something with no everyday equivalent. These are not exotic edge cases. They are among the most common planet types in the galaxy, and by virtue of having no example in our own solar system, they remain poorly understood. The most violent events in the universe are gamma-ray bursts. In their short form, they last from a fraction of a second to about 2 seconds. In their long form, from a few seconds to several minutes. In either case, during those brief windows, they release more energy than the Sun will produce across its entire 10 billion year life. GRB 221009A, detected in October 2022, was quickly nicknamed the Boat, the brightest of all time. It saturated detectors on multiple spacecraft simultaneously, because instruments designed to record the most extreme events in the cosmos were not calibrated to handle something this bright. Its afterglow was visible to amateur astronomers through modest telescopes for days after the burst itself. The initial emission came from a collapsing massive star, with jets of material blasting outward at very close to the speed of light, focused into a narrow beam that happened to point directly at Earth. Photons from that burst with energies in the tera-electron-volt range, far above anything detectable in most gamma-ray observatories, were captured by the LHAASO telescope in China, representing the highest energy photons ever detected from a gamma-ray burst. What makes GRB 221009 a scientifically remarkable beyond its brightness is that some of the ultra-high energy photons were analyzed for signatures of quantum gravity. Some theoretical models predict that space-time, at the Planck scale, is not smooth, that it has a granularity that would cause photons of different energies to travel at very slightly different speeds. Over cosmological distances, that tiny difference would accumulate into a measurable arrival time offset. Photons from GRB 221009A arrived with timing consistent with all energies traveling at the same speed, placing new constraints on how granular space-time can be. The universe fired its most powerful known shot in our direction, and in the process, handed physicists a precision instrument for probing the structure of space itself. Short gamma-ray bursts lasting under 2 seconds come from a different process entirely. The leading model is the merger of two neutron stars, or a neutron star and a black hole. On August 17, 2017, for the first time in history, a gravitational wave event and a gamma-ray burst were detected simultaneously from the same location in the sky. The gravitational wave signal, GW170817, arrived at the LIGO and Virgo detectors, followed 1.7 seconds later by a short gamma-ray burst detected by the Fermi and Integral satellites. The gap of 1.7 seconds, over a travel distance of approximately 130 million light-years, constrained how closely the speed of gravitational waves matches the speed of light. The result, within 1 part in 10 to the power of 15, gravitational waves and light travel at the same speed to a precision far beyond any previous test. That single coincident detection ruled out entire classes of modified gravity theories overnight. Models that had been built over years to explain cosmological anomalies without dark energy were eliminated in hours because they predicted gravitational waves would travel at a different speed than light. The universe's most violent events are also its most precise physics experiments. Dark energy is the name given to whatever is causing space to expand at an accelerating rate. It was first confirmed in 1998 when 2 independent teams studying Type Ia supernovae found that distant supernovae were dimmer than expected. They were farther away than a decelerating or even a coasting universe would place them. The universe wasn't just expanding. It was speeding up. The source of that acceleration is assigned a placeholder name, dark energy. And in the standard model, it takes the form of a cosmological constant, a fixed energy density inherent to space itself, uniform across all of space-time, unchanging over time. When dark energy was first inferred, this was already strange enough. The value of the cosmological constant, the energy density of empty space, is something that can, in principle, be calculated from quantum field theory. Quantum field theory predicts that the vacuum is not empty. It is filled with a seething background of virtual particles constantly appearing and disappearing on timescales too short to violate the uncertainty principle. All of those quantum fluctuations contribute energy to the vacuum. When you calculate how large that vacuum energy should be, based on known particle physics, you get a number. And when you compare that number to the observed value of the cosmological constant inferred from the accelerating expansion of the universe, the ratio between prediction and observation is approximately 10 to the power of 120. The prediction is off by 120 orders of magnitude. That is not a minor discrepancy. It is the largest known disagreement between theory and observation in all of physics. The reason the universe is not infinitely curved by vacuum energy, the reason it exists in any recognizable form at all, requires that the contributions from different quantum fields cancel each other to a precision of 120 decimal places. Why that cancellation happens, and why it leaves a tiny but non-zero residual that is exactly large enough to cause the late-time acceleration we observe. That is called the cosmological constant problem, and it has resisted solution since the problem was clearly articulated. Then, in early 2024, results from the Dark Energy Spectroscopic Instrument DESI, measuring the expansion history of the universe through baryon acoustic oscillations, suggested something more complicated. The DESI data, when combined with other cosmological datasets, showed mild but potentially significant evidence that dark energy is not constant, that its strength may have varied over cosmic time. If dark energy is dynamic rather than fixed, if it has changed, and might change again, then the fate of the universe is no longer simply a slow fade. The behavior of the universe and its deep future depends on the detailed physics of something we don't yet understand. A cosmological constant is one of the simplest possible forms dark energy could take. Evidence that it isn't constant is evidence that there is more to learn, and that the equations governing the very largest scale behavior of reality are still missing terms. Dark matter makes up roughly 27% of the universe's total energy content. Ordinary matter, everything that can be seen, touched, and measured, makes up only about 5%. The remaining 68% is dark energy. Dark matter does not interact with light in any way we can detect. It does not emit, absorb, or reflect electromagnetic radiation. The only way we know it exists is through its gravitational effects. Galaxies rotate at speeds that, according to Newtonian and relativistic gravity applied to visible mass alone, should cause them to fly apart. The outer stars of a galaxy like the Milky Way move just as fast as the inner ones, a rotation curve that is flat rather than declining with distance. The only way to reconcile that with known physics is to surround each galaxy in a vast halo of invisible mass, extending far beyond the visible disk. The Bullet cluster provided one of the most direct pieces of evidence. Two galaxy clusters pass through each other. The hot gas in each cluster slammed together and slowed, left behind in the collision zone. But gravitational lensing, the bending of background light by mass, showed that the majority of each cluster's mass kept moving forward, passing through the collision undisturbed, as if nothing had happened. The hot gas slowed because electromagnetic interactions created drag. The dark matter kept going because it has none. Despite decades of searching, no direct detection of a dark matter particle has been confirmed. Every purpose-built underground detector, shielded from cosmic rays by kilometers of rock, looking for the faint nuclear recoil that a dark matter particle might produce, nothing confirmed. The Large Hadron Collider, which can probe energies at the scale where many dark matter candidates were predicted to appear, nothing. Weakly interacting massive particles, once the leading theoretical candidate, have been pushed into increasingly narrow corners of parameter space. New candidates, axions, sterile neutrinos, primordial black holes are being tested. What dark matter actually is remains one of the most consequential unsolved problems in physics. It shapes every galaxy, determines the large-scale structure of the universe, and constitutes more than a quarter of everything, and it has so far refused to reveal itself through any channel except gravity. The situation is made stranger by an observation known as the missing satellites problem. Simulations of dark matter halo formation predict that a galaxy like the Milky Way should be surrounded by thousands of small satellite galaxies, condensations of dark matter that collected enough ordinary matter to form stars. Observations find far fewer. There are dozens of confirmed satellites of the Milky Way, and ongoing surveys keep finding small ones, but the number still falls substantially short of the prediction. Proposed resolutions involve various astrophysical processes: supernova feedback, ejecting gas from small halos before stars can form, tidal stripping by the Milky Way's gravity, reionization, heating gas, and preventing it from falling into small halos. These processes are plausible and likely contribute. But whether they fully account for the discrepancy, or whether the dark matter model needs modification, is still being worked out. The universe is expanding. That fact has been established since the 1920s, when Edwin Hubble's measurements of distant galaxies revealed that they recede at velocities proportional to their distance. The rate of this expansion is described by the Hubble constant, and for decades, determining its precise value was one of the central projects of observational cosmology. The problem is that two fundamentally different methods of measuring the Hubble constant give two fundamentally different answers. Measurements based on the cosmic microwave background light left over from when the universe first became transparent, roughly 380,000 years after the Big Bang, yield a value of approximately 67.4 kilometers per second per megaparsec. Measurements based on the local universe using type Ia supernovae as standard candles to measure distances, calibrated by Cepheid variable stars, yield approximately 73 kilometers per second per megaparsec. The difference is roughly 9%. In a field where measurements have achieved sub-percent precision, a 9% discrepancy between two independently derived values for the same fundamental constant is not a rounding error. This is called the Hubble tension, and it has now reached a statistical significance above 5 sigma, meaning there is less than a 1 in a million chance. The disagreement is due to random measurement error. Both methods have been scrutinized exhaustively for systematic errors. New distance indicators have been brought in. The James Webb Space Telescope has re-examined the Cepheid calibration step in the local distance ladder with far greater resolution than previously possible, largely confirming the local measurement rather than pulling it toward the CMB value. The tension has not resolved. If both measurements are correct, then one of two things must be true. Either there is some unknown systematic effect biasing one or both measurements, something that has evaded detection across multiple independent methods, and multiple generations of instruments. Or there is new physics between the early universe and the late universe that the standard cosmological model does not account for. What that new physics might be is genuinely unknown. Proposals include early dark energy, an additional component, active only in the very early universe, modifications to general relativity, new light particles, or our location inside a large, underdense region of space that inflates local recession velocities. None of these proposals has yet risen to the level of consensus. The Hubble tension sits as an open wound in the otherwise remarkably successful standard model of cosmology, a number that shouldn't disagree with itself. Disagreeing with itself at 5 sigma. The lithium problem is one of the quietest mysteries in astrophysics. It does not involve extreme energy or unprecedented structures. It involves a simple disagreement between two well-established lines of evidence that has persisted for more than 4 decades. In the first few minutes after the Big Bang, the universe was hot and dense enough for nuclear reactions to occur. This period is called Big Bang nucleosynthesis, and it lasted roughly 20 minutes. During that time, protons and neutrons fused to create the lightest elements: hydrogen, helium, and trace amounts of lithium-7. The proportions of these elements predicted by Big Bang nucleosynthesis, given the measured density of baryonic matter in the universe, match observations with extraordinary precision for hydrogen and helium. But for lithium-7, the prediction is a factor of 3 too high. The oldest, most primitive stars, population 2 stars, in the galactic halo, formed early in the universe from nearly pristine material, show a lithium-7 abundance that is consistently about 1/3 of what nucleosynthesis predicts. This isn't a measurement of 1 or 2 stars. It has been confirmed across hundreds of stars in the galactic halo, with a consistency that has earned it the name the Spite Plateau, named for astronomers Monique and Francois Spite, who identified it in the 1980s. 3 times too much lithium-7 predicted. 1/3 of it actually observed. In all the years since, nobody has found a completely satisfying explanation. The candidates are a nuclear reaction rate in early stellar interiors that destroys lithium more efficiently than models account for, a mechanism that depletes lithium in the surface layers of old stars, hiding it from spectroscopic observation, or an error in the nucleosynthesis calculations themselves. None of these explanations is fully supported by independent evidence. New physics, beyond the standard model of particle physics, could in principle alter the nucleosynthesis calculations. Some researchers have explored whether a resonance in beryllium-8 could redirect the nuclear pathway away from lithium-7 production. But no such resonance has been confirmed in laboratory experiments. The lithium problem is small, quiet, and decades old. But it is a clean discrepancy between theory and observation at the level of the very first nuclear reactions in the universe, sitting unresolved in the literature, while cosmology and particle physics continue to build new frameworks around it. There is a cloud near the center of our galaxy, about 26,000 light-years from Earth, known as the Sagittarius B2 molecular cloud complex. It is one of the largest molecular clouds near the center of the Milky Way, a vast reservoir of gas and dust from which stars are forming. Embedded within it is a region called Sagittarius B2 North, the North Molecular Hot Core, where astrochemists have been systematically cataloging the organic molecules present. The list is extensive. Over 200 distinct molecular species have been identified in the interstellar medium as a whole. Among them are ethanol, the same molecule found in alcoholic beverages, formaldehyde, acetic acid, methylamine, a precursor to amino acids, glycolaldehyde, a simple sugar. And in 2022, ethanolamine, a molecule that serves as a component of the lipid membranes surrounding biological cells, was detected in the interstellar medium for the first time. The presence of complex organic molecules in interstellar space is not itself a mystery. Chemistry, given enough time and sufficient concentrations of atoms like carbon, hydrogen, oxygen, and nitrogen, assembles complexity spontaneously under a wide range of conditions. What makes the Sagittarius B2 detections striking is the sheer density and variety of the chemistry taking place in an environment that should, by most intuitions, be inimical to molecular complexity. Space is cold. The molecular cloud cores hover near 10 degrees above absolute zero. Space is bombarded by cosmic rays and ultraviolet radiation. The densities involved are far lower than the best laboratory vacuums on Earth. And yet, on the surfaces of dust grains in these clouds, complex molecules form, survive, and accumulate. The molecules detected in Sagittarius B2 include the basic chemical ingredients for life as we know it assembled in the cold dark of a molecular cloud billions of years before any planet in the vicinity could have formed. The implication is that the chemistry leading to life does not begin on planets. It begins in space, long before the planets exist, and is delivered to planetary surfaces when the clouds collapse into solar systems and the dust and ice of the early nebula settles into comets and asteroids. This picture that the molecular precursors of biology are a natural product of the chemistry operating wherever carbon-rich atoms gather in sufficient quantities shifts the question of life's origin. If the ingredients are common and arrive pre-made, then the question is no longer where the raw materials come from. It becomes, what does it take to assemble them? That question doesn't have an answer yet. But the fact that the ingredients are out there, scattered across molecular clouds throughout the galaxy, changes the framework in which it's asked. The most direct detection of the strangeness of space came not through telescopes, but through machines built specifically to sense the geometry of space-time. In September 2015, the LIGO detectors registered a signal lasting about 0.2 of a second, a brief chirp that swept upward in frequency before disappearing. The signal was a gravitational wave. It had been produced 1.3 billion light-years away by the merger of two black holes, one approximately 29 solar masses and one approximately 36 solar masses, spiraling into each other and colliding. In the final fraction of a second before merger, the power radiated in gravitational waves exceeded the combined luminous power of every star in the observable universe by a factor of roughly 50. The resulting merged black hole had a mass of approximately 62 solar masses. The missing 3 solar masses, the difference between 65 combined solar masses of the original pair and 62 solar masses of the result, were converted directly to gravitational wave energy and radiated into space in that fraction of a second. 3 solar masses of energy, gone, in less time than it takes to blink. The LIGO detectors, with arms 4 kilometers long, registered a displacement of the mirrors at each end of less than 1,000th the diameter of a proton. That measurement, detecting a change in length that is 1 billion times smaller than the smallest atom, is one of the most precise measurements ever made by any instrument in human history. Since 2015, dozens of gravitational wave events have been detected. Binary black hole mergers, binary neutron star mergers, and several sources that belong to the mass gap like GW190814, whose identities remain uncertain. Each event is a piece of a census of compact objects in the universe, assembled by listening to vibrations in the fabric of space-time itself. The universe speaks in a channel we had no instruments to receive until very recently. And the first sentences we heard were stranger than expected mergers at masses, mass ratios, and distances that challenged population models built from electromagnetic observation alone. In 2023, the North American Nanohertz Observatory for Gravitational Waves, NanoGrav, released results from 15 years of pulsar timing data. Together with 4 other pulsar timing array collaborations around the world, they reported strong evidence for a gravitational wave background, a persistent, low-frequency gravitational wave signal present in all directions of the sky. Not from a single catastrophic event, not from a single source, but a background hum woven through the fabric of space-time, coming from everywhere at once. The leading interpretation is that the background is generated by an enormous population of supermassive black hole binary systems across the observable universe, pairs of black holes, each with masses ranging from millions to billions of solar masses, in the final stages of spiraling together before merger. There could be hundreds of thousands of such pairs, each emitting gravitational waves at low frequencies as they slowly lose orbital energy. The superposition of all their emissions creates the background signal detected in the pulsar data. For 15 years, a network of pulsars scattered across the galaxy, each one a natural clock, each one tracking tiny distortions in spacetime as gravitational waves rolled through, was recording it. The gravitational wave background is evidence that supermassive black hole mergers are a common feature of the universe's history, happening continuously across cosmic time. Every galaxy merger eventually drives 2 central black holes together. And the timescales for that final coalescence are playing out across the cosmos right now, broadcasting in a frequency we are only just learning to hear. There is a type of star so extreme that it represents the most magnetic object confirmed to exist anywhere. Magnetars are a subclass of neutron star. They form the same way from the core collapse of a massive star at the end of its life. But magnetars develop magnetic fields of extraordinary strength during formation. Through a process that likely involves an extremely rapid initial rotation and a dynamo mechanism in the first seconds of the neutron star's life. The magnetic field of a typical neutron star is roughly 1 trillion times stronger than Earth's. A magnetar's field is another 1,000 times beyond that, reaching values of around 10 to the power of 15 Gauss. For reference, the most powerful continuous magnetic fields sustained in laboratory experiments are around 45 Tesla, which is 450,000 Gauss. A magnetar's field is on the order of 10 billion Tesla. That field contains so much energy that it continuously stresses and distorts the neutron star's rigid crystalline crust. When the crust cracks a starquake, the magnetic field restructures violently, releasing energy in a burst of X-rays and gamma rays that can be detected across the galaxy. On December 27, 2004, a magnetar designated SGR 1806-20, located about 50,000 light-years away, released a burst of gamma rays that lasted about 0.2 of a second. In that fraction of a second, it released more energy than the Sun produces in 250,000 years. The burst hit Earth's upper atmosphere and briefly ionized the ionosphere at night, the same ionospheric layers that only solar radiation can normally affect. For a moment, a neutron star 50,000 light-years away altered Earth's electrical environment. In 2020, the first fast radio burst from within the Milky Way was traced to a magnetar, SGR 1935 plus 2000, 154. Fast radio bursts are millisecond duration radio pulses of extraordinary brightness. First detected in 2007 in archival data. For years, their origin was entirely unknown. Their brightness implied sources of cosmological distance, billions of light-years releasing enormous energy. But their rapid duration meant the source had to be physically compact, no larger than a few hundred kilometers. The detection of a fast radio burst from a Milky Way magnetar was the first direct link between a known class of object and these mysterious signals. The mechanism by which magnetars produce fast radio bursts is not yet fully understood. But the confirmation that at least one did came as a significant step in one of astronomy's most active unsolved questions. What powers the brightest, brief radio signals in the cosmos? Some fast radio bursts repeat, others appear only once and then never again. Some repeating ones show patterns, periodic windows of activity, alternating with periods of silence, while others appear to burst irregularly. A handful of repeating sources have been localized precisely enough to identify their host galaxies. They appear to prefer star-forming regions, consistent with young magnetars. But the full diversity of fast radio burst behavior, the range of energies, the variety of temporal structure, the mix of repeating and non-repeating events suggests the population may not be uniform. There may be multiple mechanisms. There may be multiple source types. The universe may be broadcasting in millisecond radio pulses from more than one kind of cosmic transmitter. In early 2023, the James Webb Space Telescope began returning images that forced a serious reconsideration of what the early universe looked like. Multiple galaxies were found at redshifts above 10, meaning we are seeing them as they appeared when the universe was less than 500 million years old. Some of them were brighter, more massive, and more structured than existing models predicted. Galaxies at that epoch were supposed to be primitive, nascent things, small, irregular, still assembling themselves from their first generations of stars. Instead, Webb found objects that look, in some cases, surprisingly like mature structures. Galaxy Sears 2112, confirmed in late 2023, showed evidence of a barred spiral structure at a time when the universe was only about 2 billion years old. Bars in spiral galaxies are thought to take time to develop. They require a degree of gravitational organization and stability that was not expected this early in cosmic history. But more unsettling were the galaxies found at even higher redshifts, with stellar masses that exceeded what standard cosmological models predicted for their epoch by significant margins. One analysis of early Webb targets suggested that the total stellar mass, locked up in massive early galaxies, exceeded the predictions of the standard lambda CDM model, the leading framework, for structure formation by factors of 10 to 100. If those mass estimates hold under further scrutiny, they represent a genuine challenge. The standard model isn't slightly off on these objects. It is off by orders of magnitude. Not every preliminary result from Webb has survived more careful analysis, and some of the most extreme early mass estimates have been revised downward. But enough anomalously massive early galaxies remain after that scrutiny to constitute a real tension, another place where the universe seems to have assembled itself faster and more efficiently than theory allows. The tentative name for this challenge is the early galaxy problem, and it connects to the earlier puzzle of ultramassive black holes appearing too early. Both suggest that the processes of mass assembly in the universe's first billion years were somehow more efficient or operated differently than the standard model of structure formation predicts. Whether this requires new physics, or whether it will eventually be explained by astrophysical processes, not yet fully modeled in simulations, like feedback from early supermassive black holes, shaping the surrounding galaxy in ways existing codes don't capture, is an active area of research with no resolution yet in sight. Not all of the strangest things in space are enormous. Some are small, or at least compact, and strange in their density. A white dwarf is what remains when a star of moderate mass ends its life. The outer layers are expelled in a planetary nebula, and the core remains, a dense ball of carbon and oxygen, roughly the size of Earth but containing roughly the mass of the Sun. The surface temperature, when first formed, can exceed 100,000 degrees Celsius. But white dwarfs have no energy source. They are simply cooling over time. In 2019, astronomers studying a sample of white dwarfs with the Gaia Space Telescope found something unexpected. In the color magnitude diagram, a chart of how bright something is against how hot it is, white dwarfs of a certain age appeared to cluster together at a particular temperature, rather than being distributed continuously as cooling theory predicted. The leading explanation was crystallization. As a white dwarf cools below roughly 10 million degrees in its core, the carbon and oxygen ions it contains begin to arrange themselves into a crystal lattice, the first stage of the white dwarf, solidifying into what would eventually be a planet-sized diamond. The crystallization releases latent heat, slowing the cooling process and causing white dwarfs going through this phase to appear to linger at the same temperature for longer than expected. The signal in the Gaia data was consistent with this, a pileup of white dwarfs releasing their crystallization heat, essentially a queue of objects waiting to finish solidifying. Our own Sun, roughly 5 billion years from now, will end this way. Its remnant core will cool over tens of billions of years and eventually crystallize into a body made largely of carbon crystal, a cold, dark object the size of Earth, embedded in the void. There is a white dwarf already in this state, or approaching it, at the center of the pulsar system, PSR J2222-0137, about 870 light-years away. It is one of the coolest white dwarfs ever detected so cold, it is essentially invisible in optical wavelengths, only detectable because its companion neutron star provided a way to calculate where to look. The universe makes diamonds. It just does it on timescales of hundreds of billions of years, in the corpses of stars that burned for billions of years before going quiet. The process is not instantaneous. It is the slowest transformation of matter at cosmological scale, a solid-state phase transition in an object the size of a planet, occurring over timescales longer than the current age of the universe. The oldest white dwarfs in globular clusters are still in the process of crystallizing. The ones that formed from the very first generation of stars have not yet cooled far enough. When the universe is many times older than it is now, these objects will have completed their transformation. The galaxy will be scattered with cold, dark, crystallized stellar remnants, invisible to any telescope, sensitive only to visible light, silent in every wavelength, drifting through space as the most patient objects the universe has ever made. One of the most counterintuitive properties of the universe sits quietly at the heart of how we understand its geometry. The universe appears to be flat. Not flat in the everyday sense, not a surface or a plane, flat in the sense that the geometry of space, on large scales, follows Euclidean rules rather than the rules of a positively or negatively curved manifold. Measurements of the cosmic microwave background, particularly the positions and amplitudes of the acoustic peaks and the temperature fluctuations, are sensitive to the overall curvature of the universe. The data from satellites like WMAP and Planck show that the universe is flat to within measurement precision of about 0.5%. For the universe to be this flat, the total energy density matter, radiation, and dark energy combined must be extremely close to the critical density, the specific value at which the geometry is exactly flat. That this density should be so precisely tuned, given that the universe has been evolving for 13.8 billion years, during which small initial deviations from flatness would have grown dramatically, is one of the motivations for the theory of cosmic inflation. Inflation, an extraordinarily rapid expansion of space in the universe's first fraction of a second, predicts that whatever curvature existed before inflation would be stretched so far that any local region of the universe, including everything we can observe, would appear flat. It also predicts specific features in the CMB power spectrum that have been confirmed. But inflation itself raises questions it doesn't answer cleanly. What drove inflation? How did it start? How did it end? The inflaton, the hypothetical field responsible, has no confirmed laboratory detection. Its properties are constrained by CMB observations, but its nature is unknown. And some models of inflation predict that it continues eternally in some regions of the universe, with our observable cosmos being one bubble in an infinite sea of inflating space. The flatness of the universe is a clue pointing toward inflation, and inflation points toward a universe far larger and far stranger than anything that can be directly observed. If the inflationary multiverse is real, if our observable universe is one bubble among an uncountable number of others, then the constants of nature in each bubble may differ. The electron mass, the strength of the electromagnetic force, the value of the cosmological constant, these could be different in other bubbles. The fact that they take the values they do in our bubble, values that happen to allow atoms, stars, planets, and observers, would then be a selection effect rather than a fundamental law. We observe the values we do because only certain values allow observers to exist. This is called the anthropic principle, and it is deeply controversial. Some physicists find it intellectually unsatisfying. It replaces explanation with selection. Others find it unavoidable. If the multiverse exists and physical constants vary, selection effects are real. The multiverse is not currently testable. It may never be, but its existence is a logical consequence of inflation, which is the leading solution to the flatness and horizon problems of standard cosmology. The universe's flatness leads, through a chain of inference, to the possibility that ours is not the only one. The universe, at every scale and in every direction we look, keeps producing things that fit poorly into whatever framework we most recently thought we understood. Structures too large to exist by the rules of cosmological homogeneity. Black holes too massive to have formed in the time available. Objects of unknown identity falling in the gaps between known categories. Rain made of iron on worlds with no day and no night. Rain made of glass on a blue planet thousands of degrees hot. A universe whose expansion rate cannot agree with itself. Organic molecules assembled in molecular clouds where nothing should be able to form. Gravitational waves, from mergers powerful enough to radiate entire solar masses of energy in fractions of a second. Crystals forming from dead stars over timescales that dwarf the current age of the universe. A continuous background hum in the geometry of spacetime, generated by some of the universe's most massive objects, slowly falling toward each other across every direction of the sky. Galaxies assembled in the universe's first few 100 million years at masses that should have taken billions of years to accumulate. A lithium abundance in the oldest stars that disagrees with the predictions of the Big Bang by a factor of 3, with no confirmed explanation after 4 decades of searching. Cold spots in the first light of the universe that statistical models struggle to account for. Anomalies in the CMB that persist after every known systematic effect is removed. And a cosmological constant, the energy of empty space that is simultaneously the most successful prediction in cosmology and the most catastrophically incorrect prediction in the history of physics, depending on which calculation you compare it to. Each of these things has been found precisely because observation has become so precise, so sensitive, and so wide-ranging that the places where theory and reality diverge are now measurable. A discrepancy can only be seen if the measurement is good enough to see it. The fact that anomalies keep appearing is not a sign that physics is failing. It is a sign that physics is doing its job, finding the seams, identifying the gaps, and building better descriptions of what is actually out there. Every generation of instruments has revealed a universe more complex than the one before it. The Hubble Space Telescope showed us galaxies at the edge of the observable universe. LIGO heard space vibrate. The Event Horizon Telescope resolved the shadow of a black hole 6.5 billion solar masses across. The James Webb Space Telescope is showing us the universe's first galaxies and finding them stranger than predicted. The next generation, the Extremely Large Telescope, the Vera Rubin Observatory, the Laser Interferometer Space Antenna. The Habitable Worlds Observatory will not find a universe that finally looks the way we expected. One of the most enduring mysteries in stellar physics involves something that should be straightforward. The sun is hot. Its surface, the photosphere, has a temperature of about 5,500 degrees Celsius. That makes sense. Nuclear fusion in the core generates enormous energy, which radiates outward and heats the surface. But the corona, the outermost layer of the sun's atmosphere, extending millions of kilometers into space, has a temperature of around 1 million to 3 million degrees Celsius. The corona is hundreds of times hotter than the surface. And that is the opposite of what every intuition about heat flow would suggest. Heat moves from hot to cold, not from cold to hot. The surface of the sun is hotter than the layers above it. So by any conventional understanding of thermodynamics, the corona should be cooler than the photosphere, not hundreds of times hotter. It isn't. This is called the coronal heating problem, and it has been a genuine puzzle in astrophysics since the corona's extreme temperature was first measured in the 1940s. The most widely discussed mechanisms involve waves and magnetic reconnection. Magnetic waves, Alfvén waves, propagate along the sun's magnetic field lines from the surface into the corona, carrying energy. When they dissipate, that energy heats the surrounding plasma. Magnetic reconnection events, sudden releases of stored magnetic energy when field lines snap and reconnect in new configurations, also inject energy into the corona as impulsive heating events. Both mechanisms likely contribute. The Parker Solar Probe, which has made the closest approaches to the sun ever achieved by a spacecraft, has detected the signatures of Alfvén waves propagating outward from the surface. The Solar Orbiter spacecraft has separately identified small-scale magnetic reconnection events called campfires, flickering across the sun's lower atmosphere. Both findings point toward the same energy channel. But whether these processes alone are sufficient to maintain corona temperatures, and in what proportions, is still being quantified. The sun has been burning for roughly 4.6 billion years. Every star of comparable type, every sun-like star in every galaxy in the observable universe almost certainly has a hot corona for the same physical reasons. And for the entire time that the sun has been hot enough to support planets, liquid water, and ultimately life, this fundamental asymmetry in its atmospheric temperature has persisted unexplained. Somewhere in the universe right now, a star is vanishing, not exploding, not fading. Simply there, one moment, gone the next, at least from our perspective. In 2019, astronomers reported the disappearance of a massive star in the galaxy, PHL 293b, located approximately 75 million light-years away. The star had been observed in earlier surveys. It was a luminous blue variable, one of the most massive and luminous stellar types that exist, with a mass around 100 times that of the Sun and a luminosity millions of times greater. When researchers returned to examine the galaxy with the Hubble Space Telescope and other instruments, the star was not there. One proposed explanation is a failed supernova. In standard stellar evolution, a massive star ends its life in a catastrophic supernova explosion that can briefly outshine an entire galaxy. But theory predicts that some massive stars, particularly those above a certain mass threshold, may undergo core collapse without a successful explosion. The energy released in the collapse may be insufficient to eject the outer layers, or the dynamics may simply not produce the outward shock needed to generate a visible explosion. Instead, the star collapses directly to a black hole. Its light disappears over a matter of days rather than months. From any vantage point in the galaxy, a star that was there is simply gone. If the failed supernova interpretation is correct, these events may be more common than previously recognized. Population studies suggest that a significant fraction of the most massive stars may end this way quietly, without the spectacular display of a supernova, simply collapsing into darkness. Each one would be a black hole that formed without announcement, without a gravitational wave signal detectable by current instruments, without an electromagnetic counterpart, just an absence where there used to be a star. The cosmic microwave background is the oldest light we can detect. It comes from a moment 380,000 years after the Big Bang, when the universe first cooled enough for electrons and protons to combine into neutral hydrogen. Before that moment, the universe was an opaque plasma. Photons could not travel freely because they were constantly scattered by free electrons. When recombination occurred, the universe became transparent. Photons streamed freely for the first time. Those photons have been traveling ever since, stretched by the expansion of the universe into the microwave wavelengths we detect today. They come from every direction with nearly perfect uniformity at a temperature of 2.725 Kelvin, but not perfect uniformity. Embedded in the CMB are tiny temperature fluctuations, typically around 1 part in 100,000, that correspond to the density variations in the early universe, from which all structure later formed. The physics of these fluctuations is encoded in the power spectrum, a graph showing how much variation exists at each angular scale across the sky. The power spectrum has been measured with extraordinary precision by the WMAP and Planck satellites. It shows a series of peaks and troughs, acoustic peaks, that represent the harmonics of sound waves that were propagating through the plasma of the early universe at the moment of recombination. The positions of these peaks constrain cosmological parameters with remarkable precision. They tell us the total density of the universe, the density of ordinary matter, the density of dark matter, the age of the universe, the geometry of space, all from a snapshot of light from 13.4 billion years ago. But the standard cosmological model, when fit to the CMB data, makes predictions about what the late universe should look like. And in several ways, the late universe doesn't quite match those predictions. The Hubble tension is one. Another is a discrepancy in the clustering of matter. The parameter sigma 8 measures how clumped matter is on scales of 8 megaparsecs, how much structure has developed through gravitational collapse. Measurements of sigma 8 from the CMB predict a value that is slightly higher than what is measured directly from the distribution of galaxies and galaxy clusters in the late universe. The discrepancy is smaller than the Hubble tension but points in a similar direction. The universe today looks slightly less structured than the early CMB data predicts it should be. If the discrepancy is real and not attributable to systematic measurement errors, it suggests that something slowed the growth of structure between the early universe and today, or that the model relating early conditions to late behavior is missing something. The sum of these tensions, the Hubble constant, the sigma 8 parameter, the CMB anomalies, forms a pattern that is difficult to dismiss as coincidence. Each one individually might be explainable. Together they suggest that the standard model of cosmology, as successful as it has been, may be an approximation to something more complete. The interstellar medium is not empty. Between the stars, space is filled with gas and dust at extraordinarily low densities, but not zero. In some regions, this gas is cold and dense enough to form molecular clouds. In others, it is heated by nearby stars into warm ionized plasma. And in others, it is swept into structures by supernova shock waves that race outward from stellar explosions at thousands of kilometers per second. These supernova remnants are among the most energetic objects in the galaxy. When a massive star at the end of its life undergoes core collapse, the resulting explosion releases on the order of 10 to the power of 44 joules of energy, roughly equivalent to the total output of the Sun over its entire 10 billion-year lifetime, released in a matter of seconds. Most of that energy comes out in neutrinos particles so weakly interacting that they pass through the entire star almost unimpeded. Only about 1% of the energy couples to the stellar envelope and drives the explosion. That 1% is sufficient to accelerate the outer layers of the star to velocities of thousands of kilometers per second. Those layers expand outward as a shell of hot, ionized gas, plowing into the surrounding interstellar medium and sweeping it into a dense wall of compressed gas. The resulting supernova remnant glows across the electromagnetic spectrum for thousands of years. In the interior of the remnant, the shock-heated gas reaches temperatures of tens of millions of degrees. In the outer shell, the swept-up interstellar gas is compressed into filaments and sheets. The interface between the two is unstable, prone to the Rayleigh-Taylor and Kelvin-Helmholtz instabilities that generate the complex, knotted, filamentary structures visible in images of remnants like Cassiopeia A and the Crab Nebula. The Crab Nebula is the remnant of a supernova observed and recorded in the year 1054 by astronomers in China, Japan, and the Islamic world. At its center sits the Crab pulsar, the neutron star produced by the explosion, spinning at about 30 revolutions per second. The pulsar's rotation powers a nebula of relativistic electrons and magnetic fields, a pulsar wind nebula that illuminates the surrounding remnant with X-ray and optical emission. The pulsar is slowing down at a measurable rate as it loses rotational energy into the surrounding nebula. That energy comes out as radiation and relativistic particle acceleration. The Crab pulsar alone powers the luminosity of the entire Crab Nebula, a region roughly 10 light-years across by spinning down. Supernova remnants are not simply expanding shells of gas. They are particle accelerators. The shock fronts of supernova remnants accelerate charged particles to extremely high energies through a process called diffusive shock acceleration, or Fermi acceleration, where particles bounce repeatedly across the shock front, gaining energy with each crossing. The cosmic rays detected at Earth, high-energy protons and nuclei moving at close to the speed of light, arriving continuously from all directions, are thought to be produced largely by supernova remnants in our galaxy, accelerated to energies up to at least 1 peta-electron volt. The galaxy is continuously making high-energy particles through the same process that recycles stellar material back into the interstellar medium. Every atom heavier than hydrogen in your body was forged in a stellar interior or in the explosive end of a star, and many of those atoms pass through supernova remnants as cosmic rays before eventually settling into the gas cloud that formed the Sun and its planets. The stars don't just go quiet, they redistribute themselves. There is a peculiar category of object that sits at the intersection of stellar physics and relativity in a way that makes them unlike anything else. Ultraluminous X-ray sources, known as ULX sources, are objects in nearby galaxies that emit more X-ray energy than any single stellar mass black hole should be able to produce. The standard interpretation for many years was that they must be intermediate mass black holes, objects with masses of hundreds to thousands of solar masses, filling the gap between stellar mass black holes and supermassive ones. That interpretation had the advantage of being straightforward. If the object is heavy enough, it can emit enough radiation to explain the observed luminosity without violating the Eddington limit. But in 2014, the X-ray satellite NuSTAR observed something unexpected in the Messier 82 galaxy. One of the brightest ultraluminous X-ray sources, M82X2, was found to be pulsing at a period of 1.37 seconds, with a brightness that varied regularly. Pulsations are the signature of a neutron star, not a black hole. Neutron stars pulse because their emission is beamed from magnetic poles that sweep past the observer as the star rotates. But the luminosity of M82X2 was roughly 100 times greater than the Eddington limit for a neutron star, the theoretical maximum a neutron star can emit. The existence of pulsating ultraluminous X-ray sources means that neutron stars can somehow exceed their Eddington limit by factors of 100 or more. This is called super-Eddington accretion, and the physics that allows it is not fully understood. Proposed mechanisms involve beaming. The emission may be channeled into a narrow cone by the magnetic field, making it appear brighter than it is from the observer's angle, combined with genuinely super-Eddington accretion enabled by the magnetic field structure near the neutron star's surface. Since the discovery of M82X2, several more pulsating ultraluminous X-ray sources have been found. The object that was thought to represent the lightest black holes, the intermediate mass regime, turns out to contain at least some neutron stars, performing in ways that exceed what basic physics said they could do. The deep universe is not static. It is dynamic at every scale and every frequency. On timescales of billions of years, galaxies merge, clusters collide, and the cosmic web continues slowly evolving. On timescales of millions of years, star clusters form, age, and dissolve. On timescales of thousands of years, supernova remnants expand. On timescales of years, X-ray binaries flare. On timescales of days, supernovae peak. On timescales of seconds, gamma-ray bursts ignite. And on timescales of milliseconds, fast radio bursts erupt. Each timescale reveals a different population of objects and processes. And the most recent surveys have systematically mapped the variable universe, the sky, as it changes, revealing phenomena that static observations cannot detect. The Zwicky Transient Facility, which monitors the northern sky repeatedly to detect objects that change in brightness, has cataloged hundreds of thousands of transient events. Among the most unusual are the luminous fast blue optical transients LFBOTs, a recently identified class of events that are extraordinarily luminous, blue in color, and decay in days rather than the weeks typical of supernovae. The first well-studied example, AT2018 Cow, nicknamed the Cow, appeared in June 2018 in a galaxy about 200 million light-years away. Within days, it reached a peak luminosity roughly 100 times brighter than a typical supernova, then faded rapidly. Its spectra were unlike any known transient. Early observations revealed extremely high expansion velocities and a very blue spectrum, suggesting extremely hot ejecta. Subsequent observations detected X-ray and radio emission consistent with central engine activity, a compact object forming at the center of the explosion, likely a neutron star or black hole, and actively accreting material. The exact mechanism producing LF-BOTs is still debated. Proposals include the core collapse of a massive star with a very compact progenitor, a tidal disruption event where a compact object shreds a smaller companion, or a magnetar formation event where the spin-down of a rapidly rotating neutron star powers the luminosity. What is certain is that LFBOTs represent a category of cosmic explosion that was not known before the era of systematic transient surveys. The variable universe is revealing a population of events that persistent, non-systematic observation would have missed entirely. The universe has more ways to be violent than we previously cataloged. Beyond all the objects and events described above, there is one class of discovery that carries the most personal weight: potentially habitable exoplanets. Since the launch of the Kepler Space Telescope in 2009, and subsequently the TESS mission, the catalog of confirmed exoplanets has grown from a few hundred to more than 5,500. Among these are dozens of planets that orbit within their star's habitable zone, the distance range at which liquid water could exist on the surface, with sizes consistent with rocky compositions. The TRAPPIST-1 system, announced in 2017, contains 7 known Earth-sized planets orbiting a small red dwarf star, approximately 40 light-years from Earth. 3 of these planets orbit within the habitable zone. The star is smaller and cooler than the Sun, which means the habitable zone is much closer in. All 7 planets orbit closer to their star than Mercury orbits the Sun. Tidal locking, where a planet rotates once per orbit, keeping one side permanently facing the star, is likely for the inner planets. The James Webb Space Telescope has observed the TRAPPIST-1 planets in detail, measuring their thermal emission and searching for atmospheric signatures. The innermost planet, TRAPPIST-1b, appears to lack a substantial atmosphere, consistent with the proximity to the star and possible loss of atmospheric gas over the star's long lifetime. The habitable zone planets have not yet had their atmospheres fully characterized. That work is ongoing, but the existence of the TRAPPIST-1 system forces a question that was previously theoretical to become observationally immediate. In a universe that apparently makes complex organic molecules in molecular clouds, delivers them to planetary surfaces via comets, produces rocky planets at extraordinary rates, and places some of those planets at habitable distances from their stars, is life a common outcome? Or is it extraordinarily rare, perhaps unique? The honest answer is that we don't know. We have exactly one confirmed example. Every argument about the frequency of life in the universe, every Drake equation estimate, every Fermi paradox resolution, rests on extrapolating from a sample of one. What we do know is that the prerequisites are widespread. The molecules are common. The planets are common. The habitable zones are common. Whether the jump from chemistry to biology wherever and however it occurred on Earth is easy or hard, is one of the deepest unresolved questions in science. The answer, when it comes, will change everything. The universe, at every scale and in every direction we look, keeps producing things that fit poorly into whatever framework we most recently thought we understood. Structures too large to exist by the rules of cosmological homogeneity. Black holes too massive to have formed in the time available. Objects of unknown identity falling in the gaps between known categories. Rain made of iron on worlds with no day and no night. Rain made of glass on a blue planet, thousands of degrees hot. A universe whose expansion rate cannot agree with itself. Organic molecules assembled in molecular clouds where nothing should be able to form. Gravitational waves from mergers powerful enough to radiate entire solar masses of energy in fractions of a second. Crystals, forming from dead stars on timescales that dwarf the current age of the universe. A continuous background hum in the geometry of space-time, generated by some of the universe's most massive objects slowly falling toward each other across every direction of the sky. Galaxies assembled in the universe's first few 100 million years at masses that should have taken billions of years to accumulate. A lithium abundance in the oldest stars that disagrees with the predictions of the Big Bang by a factor of 3, with no confirmed explanation after 4 decades of searching. Stars that vanish not in explosions but in silence, collapsing directly to black holes without announcement. Pulsars too bright, coronae too hot. The scale of the known universe is itself one of the strangest discoveries ever made. For most of human history, the universe was the sky overhead, the sun, the moon, a scattering of planets, and stars fixed like points of light in a sphere surrounding Earth. The idea that those points of light were themselves suns, some larger and brighter than ours, some dimmer and smaller, many with their own planetary systems, is not ancient wisdom. It became convincingly established only in the 20th century. The idea that the Milky Way was one galaxy among billions, each containing hundreds of billions of stars, scattered across a space so vast that the light from the farthest visible galaxies has been traveling since before Earth existed. That idea is less than 100 years old. In 1924, Edwin Hubble measured the distance to the Andromeda Nebula using Cepheid variable stars and established that it lay far outside the boundaries of the Milky Way, roughly 2.5 million light-years away. That single measurement changed the known scale of the universe by a factor of millions overnight. What had been thought to be a nebula within our galaxy was an entire galaxy, comparable in size to our own, viewed across an inconceivable distance. And Andromeda was just the nearest large neighbor. The universe, it turned out, contained galaxies in every direction, to the limit of every instrument built to look for them. The Hubble Deep Field's long-exposure images pointed at tiny blank patches of sky, revealed thousands of galaxies in regions previously thought to contain almost nothing. The observable universe contains an estimated 2 trillion galaxies, revised upward from earlier estimates of hundreds of billions when surveys began accounting for the faint, small galaxies at high redshift. 2 trillion. Each one a system of billions to hundreds of billions of stars. Each one, potentially, containing planetary systems. The census of what exists is not complete. The census may never be complete. The most distant, observable events are so far away that the light reaching us today left its source when the universe was a small fraction of its current age. And beyond the observable horizon, the distance beyond which light has not had time to reach us since the Big Bang, the universe continues, for an unknown extent, possibly infinitely. The visible sky, in every direction, to every depth that instruments can probe, is a window into a structure so large that the word large fails to carry any meaningful weight. What this means for the question of life, of intelligence, of whether the universe is in some sense aware of itself through the observers it produces, is something no one can yet answer. The question of what happens at the very end of a star's life is not fully settled for every mass range. For stars much more massive than the Sun above, approximately 40 to 50 solar masses, the picture is complicated by the enormous luminosity and stellar winds these objects produce. Throughout their lives, a very massive star can lose much of its mass in stellar winds before it ever reaches the supernova stage. The mass lost affects the eventual outcome, how much is left, what kind of remnant forms, how the explosion proceeds. For the most massive stars above, roughly 150 solar masses, a different fate may await. In stars this extreme, the core temperatures during late-stage evolution become high enough that thermal energy can spontaneously create electron-positron pairs. This process drains energy from the radiation pressure that supports the star, triggering a rapid collapse, followed by explosive nuclear burning that can either partially disrupt the star in a pulsational pair instability supernova or completely destroy it in a pair instability supernova with no remnant. A pair instability supernova leaves nothing behind. The star is entirely dispersed. No neutron star, no black hole, just an expanding cloud of heavy elements flung into the surrounding space at enormous velocity. These events are expected to be among the most luminous supernovae possible, releasing 10 times or more the energy of a typical core collapse supernova in optical light. Candidate pair instability supernovae have been identified, including SN 2006 GY, one of the most energetic supernovae ever observed, though the pair instability interpretation remains debated. If confirmed, these events represent the complete conversion of stars, potentially hundreds of times the mass of the Sun, into dispersed gas and radiation. The most massive objects in the universe turned entirely to nothing. For stars below about 8 solar masses, which includes the vast majority of all stars, the end is quieter. A red giant phase, a planetary nebula, a white dwarf. But even here there are surprises. White dwarfs that accrete material from a companion star can reach a critical mass, the Chandrasekhar limit, approximately 1.4 solar masses, beyond which electron degeneracy pressure can no longer support them. At that point, the white dwarf undergoes runaway nuclear fusion in a thermonuclear explosion, a type Ia supernova. Unlike core collapse supernovae, which vary somewhat in their peak brightness, type Ia supernovae reach a relatively consistent maximum luminosity determined by the physics of the explosion. This consistency is what makes them standard candles, objects of known intrinsic brightness that can be used to measure cosmic distances. The discovery of dark energy in 1998 relied entirely on type Ia supernovae as distance indicators. The cosmological constant problem, the accelerating universe, the fate of everything, all of that rests on observations of white dwarfs that crossed a mass threshold and exploded in other galaxies millions or billions of light-years away. The end of a star became the tool that revealed the most fundamental property of space-time. There are signals arriving at Earth from beyond the solar system that no one fully understands. Ultra-high-energy cosmic rays are protons and atomic nuclei that arrive at Earth with energies exceeding 10 to the power of 20 electron volts. These particles carry more kinetic energy than a cricket ball moving at 70 kilometers per hour, compressed into a single subatomic particle. Their existence was confirmed in 1962 when physicist John Lindsley detected a cosmic ray event at the Volcano Ranch Array in New Mexico that registered energy of about 10 to the power of 20 electron volts. At that energy, a proton is traveling so close to the speed of light that even on cosmic timescales it barely slows down. The problem is where they come from. At these energies, protons interact with the cosmic microwave background radiation through a process called pion photoproduction, knocking a pion out of the proton, which carries away energy. This interaction is efficient enough that a proton above about 5 times 10 to the power of 19 electron volts loses most of its energy over a path length of roughly 50 megaparsecs, 160 million light-years. That means the highest energy cosmic rays, if they are protons, must come from sources within about 160 million light-years of Earth. The Auger Observatory in Argentina, the largest cosmic ray detector ever built, has measured the arrival directions of the highest energy events and found some statistical concentration around directions consistent with nearby active galactic nuclei galaxies with actively accreting supermassive black holes. But the correlations are not strong enough to identify specific sources unambiguously. The composition of ultra-high energy cosmic rays remains uncertain. They may be primarily protons, or a mix of heavier nuclei like iron, with different source requirements. And the acceleration mechanism, whatever it is that imparts energies 10 million times higher than anything the Large Hadron Collider can produce to individual particles, is not definitively known. Supermassive black holes at the centers of active galaxies are the leading candidate. The jets produced by these objects can, in principle, accelerate particles through the Fermi mechanism to extreme energies. But the specific environments, the specific geometry, the specific details that allow such enormous energies to be reached in individual particles have not been pinned down. Cosmic rays were discovered in 1912. More than a century later, the highest energy ones are still arriving, still being detected, and still not fully explained. The universe is accelerating particles to energies we cannot reproduce in any laboratory and sending them here. We detect them when they hit the atmosphere and create showers of secondary particles that we can count. But what makes them, and exactly where, remains partly open. There is a phenomenon at the boundary between physics and philosophy that the universe demonstrates in concrete, measurable ways: quantum entanglement. When two particles interact in certain ways, they can become entangled, linked in a manner such that measuring a property of one instantaneously determines the corresponding property of the other, regardless of the distance between them. This is not a metaphor. It has been tested experimentally countless times, most definitively in a series of increasingly loophole-free Bell test experiments. The most conclusive experiments, including a landmark test in 2015 using entangled photons, measured at stations separated by 1.3 kilometers, with settings chosen fast enough to prevent any signal traveling at the speed of light from coordinating the outcomes, confirmed that quantum mechanics is correct. The correlations between the two detectors were stronger than any local realistic theory could produce. There is no model in which the particles have predetermined hidden properties, and in which any influence between them is limited to the speed of light, that can reproduce the observed results. The universe is non-local, at the quantum level, in a way that has no classical analog. What this means for our fundamental picture of space and causality is still being worked out. It does not allow faster-than-light communication. The outcomes of individual measurements are random, and only the correlations, which can only be verified after classical communication, reveal the entanglement. But it does mean that the separability of distant events is not as fundamental as classical physics assumed. Two particles, no matter how far apart, can be correlated in ways that cannot be explained by any local mechanism. Astronomers have used this property to perform quantum cryptography tests over record distances, and there are proposals to use entangled photons from astrophysical sources, quasars, billions of light-years away, as random number generators, to close the final loopholes in Bell tests. The universe, at its most fundamental level of description, is not separable in the way that large-scale experience suggests. Entanglement is real. Its implications for our picture of space, time, and causality are still unfolding. Each discovery in this list was made with instruments conceived by people who didn't know what those instruments would find. The LIGO mirrors were polished to tolerances that wouldn't have seemed necessary before the goal was to measure a distortion smaller than a proton. The Event Horizon Telescope network was assembled to resolve a shadow in a galaxy 55 million light-years away, using a technique that required coordinating observations across the entire diameter of Earth. The James Webb Space Telescope was built with a mirror folded like origami to fit inside a rocket fairing, unfolding in space to collect light from the earliest galaxies. Each of these instruments found something unexpected. That is not a coincidence. It is the reliable signature of observation pushing past the frontier. Every generation of instruments has revealed a universe more complex than the one before it. The next generation, the Extremely Large Telescope, the Vera Rubin Observatory, the Laser Interferometer Space Antenna, the Habitable Worlds Observatory will not find a universe that finally looks the way we expected. It will find the things we don't have names for yet. And the process will do what it has always done: replace comfortable approximations with something more accurate, more demanding, and more astonishing. The universe has never once looked the way we predicted from the inside. It has only ever looked, in retrospect, like exactly what it is: something vastly larger, older, and stranger than any framework built by minds that evolved to navigate a single planet could have anticipated. That's not a failure of science. That is what science is for. And if the pattern holds, and it has held without exception since the first telescope was pointed at the sky, whatever we find next will be stranger still.